Today we will learn about overfitting and underfitting, a deep dive into model generalization in machine learning. Core concepts. The two fundamental pitfalls in model training are too complex or too simple. Diagnosing overfitting. High variance, low bias. Model is too complex and learns the noise and random fluctuation in the training data. Performs exceptionally well on training data, low error, fails to generalize to new unseen data, significantly high test error. The model has memorized the training set, not learned the underlying pattern. Diagnosing underfitting. High bias, low variance. Model is too simple, cannot capture the essential patterns on relationship, performs poorly on both training and test data, high error on both. Results from an overly constrained or simple model architecture that is linear model for non-linear data. The model hasn't learned enough from the training set to make the reliable predictions. The bias variance trade-off. Underfitting, high bias, occurs when the model is too simple and makes systematic errors. The predictions are consistent but inaccurate. Overfitting, high variance, occurs when the model is too complex and sensitive to small fluctuations. The predictions are scattered and unreliable. Good fit, low bias and variance. The goal is to find the optimal model complexity that minimizes the both types of error, leading to strong generalization. Identification. Using error matrix to diagnose the root cause of poor performance. Training versus test performance in underfitting, overfitting, and good fit. In underfitting, training error is high, test error is high, diagnosis is too simple. In overfitting, training error is low, test error is significantly higher, and diagnosis is too complex. In good fit, training error is low, test error is low to similar to training, and diagnosis is just right. It is balanced. Mitigation strategies. Strategic solutions for optimizing model performance and generalization. Mitigating overfitting, control complexity, regularization, introduces a penalty term to discourage overly large coefficient values in complex models. Cross-validation uses techniques like k-fold to ensure the model's performance is robust across various data subsets. Feature selection remove non-essential, noisy, or redundant input features from the dataset. Mitigating overfitting, data and architecture. Increased training data. A larger, more diverse dataset makes it harder for the model to simply memorize patterns and forces generalization. Simple the model. Reduce the number of layers or neurons in deep learning or choose a simpler base algorithm. Dropout. Randomly ignore a fraction of neurons during each training step, forcing the network to learn redundant representation. Early stopping. Stop the training process when the model's performance on the validation set begins to decline. Mitigating underfitting. Increase flexibility. Increase model complexity. Use a more flexible algorithm, for example, non-linear models, or increase the model's depth capacity to capture underlying relationships. Feature engineering. Introduce new relevant input features or create complex features by combining existing ones to better represent the target relationship. Decrease regularization. Reduce the strength of regularization L1 or L2 by being applied, allowing the model more flexibility to learn the data. Achieving good fit is very important for the performance of our model. The art of machine learning lies in finding the optimal balance between bias and variance to ensure strong generalization.